Welcome back, Trailblazers, to another Journal Club edition of the Digital Pathology Podcast. Usually when we talk about a medical diagnosis, there's this certain expectation of precision.
Oh, absolutely. It feels almost like engineering, right?
Yeah, exactly. Like you break your arm, the X-ray shows a jagged white line on a black background, and the doctor points to it and says, there it is. It's totally binary. Broken or not broken.
Right. It's clean, it's visible, and it's categorized. And, human brains just prefer that kind of definitive visual confirmation.
We really do. But, step into the world of oncology, and suddenly that clean diagnostic picture just completely shatters.
No, it shatters into a million pieces.
Right. You aren't looking at a single image anymore.
Yeah.
You are staring down this mountain of unstructured, messy information. Decades of patient history, handwritten clinic notes, dense pathology narratives.
Not to mention the constantly updating molecular report.
Yes, and the shifting clinical trial registries. It's basically diagnostic muddy waters, and it's completely overwhelming.
Which is, frankly, an information load that human cognition simply wasn't evolved to process all at once.
Right. Nobody can read all that.
Exactly. A single patient's file can span thousands of pages of text. And then you combine that with complex genomic data that literally changes meaning based on newly published research. That cognitive overload is really the focal point of our discussion today.
It is. So our mission today is to unpack a highly practical, really roadmap-focused paper titled How to Bring Generative AI to Oncology Practice.
It's a great tease.
It really is. It's by authors Truhn and J. Kather, and it was recently published in the journal ESMO Real-World Data and Digital Oncology. And, what makes this paper stand out for me is that it completely ignores the usual sci-fi hype.
Yeah, there's no Terminator stuff in here.
Exactly. It maps out the actual constraints, the IT nightmares, and the realistic trajectory for getting AI safely into the clinic.
And the central premise they establish right away is that artificial intelligence in this space is not, I repeat, not about replacing the clinician.
Crucial point.
Right. Oncology fundamentally runs on narrative texts and structured tables. So AI's role is strictly to synthesize that massive textual overload so the clinician can actually practice medicine.
Instead of spending their whole day acting as a data entry clerk.
Exactly. It's an assistant that reads across sources, tracks timelines, and, crucially, exposes its evidence.
Okay, let's unpack this. Why is generative AI, specifically large language models or LLMs, why is that the specific tool for this job? Moving from why oncology needs help to how the AI actually processes this data requires a bit of a mental shift.
It does, because these models aren't actually thinking, right? Or like looking up facts in a traditional database.
Right. They aren't Google.
Mathematically speaking, large language models are basically sophisticated sentence continuation engines. Their primary function is just to predict the next word, or more accurately, the next token in a sequence.
Just auto-completing, basically.
Essentially, yes. Based on the billions of parameters they developed during their training on vast swaths of human text, they are solving a statistical puzzle at just an unprecedented scale.
But wait, how does predicting the next word equate to doing complex medical reasoning? Because those sound like two completely different things to me.
It does sound strange, but if we connect this to the bigger picture, human language isn't just random symbols. It actually contains the underlying logic of the real world.
Okay, I see where you're going.
Yeah, so by solving these statistical puzzles so accurately, the model's internal neural network actually organizes concepts spatially. It learns that certain clinical conditions, genetic mutations, and therapeutic responses, well, they live close together in that mathematical space.
Oh, wow. So it effectively mimics medical reasoning through really complex pattern recognition.
Precisely.
Let's ground that a bit for the trailblazers listening. What does that mathematical space actually look like when applied to an oncology case?
Well, the paper uses a great example of a molecular tumor board. Imagine an LLM is processing a clinical narrative and it encounters the phrase metastatic colorectal cancer combined with a BRAV600E mutation.
Okay, pretty standard complex case.
Right. And it doesn't look up a rule book. Instead, it calculates the most statistically probable continuation of that specific semantic concept.
Because it's read so much oncology literature.
Exactly. Because of its training on all that literature, it assigns a much higher probability to a continuation involving a BRAF inhibitor, rather than one involving just standard generic chemotherapy.
Man, it's just auto-completing the clinical logic. That actually reminds me of how an experienced oncologist operates on the floor.
Oh, for sure. It's intuitive pattern matching.
Right. A seasoned doctor sees a specific cluster of symptoms, they note a few key lab results, and their brain just naturally auto-completes the picture to formulate a diagnosis.
They aren't consciously flipping through a textbook in their head.
Exactly. Their years of exposure to thousands of cases just naturally connect the dots. The LLM is doing the exact same thing, just leveraging billions of textual data parameters instead of, human clinical years.
Yeah, the underlying logic of the clinical diagnostic process and the logic of a language model map onto each other surprisingly well. They're both systems trained on massive amounts of prior examples to predict the most likely correct path forward.
But, I mean, a massive predictive text engine frozen in time has to have some serious limitations. And the paper breaks down AI complexity into 3 functional levels to explain how we actually structure these models for real-world clinical use.
Yeah, Truhn and Kather categorize LLM assistants into 3 distinct evolutionary steps. Step 1 is the standalone model.
Like early ChatGPT.
Exactly. Think of the baseline versions of early consumer AI. You put in a query, and it generates an answer entirely from the static knowledge embedded in its parameters at the exact moment its training was completed.
Which means its knowledge is permanently frozen.
Completely frozen.
So if I'm an oncologist asking a Step 1 model about a chemotherapy regimen, it might give me a perfectly fluent summary based on data from 2 years ago.
But it has zero access to the clinical trial results published yesterday.
Right. Or a recent FDA label modification. And worse, if it doesn't know the answer, the mathematical drive to predict the next word means it might just confidently fabricate an answer.
Which is what we call a hallucination.
Yeah. So a Step 1 model is essentially a medical student taking a closed book exam. Whatever they crammed into their head before the test is literally all they have.
That's a perfect analogy. And the utility of standalone models for a fast-moving field like oncology is exhausted almost immediately. Which brings us to Step 2, retrieval augmented generation, or RAG.
RAG, yeah. We hear that term a lot.
Right. In a RAG system, the underlying language model is still fixed, but we give it an external mechanism to pull in new information.
Okay, how does that work in practice?
When you ask it a question, the system first runs a search against a continually updated external database like current clinical guidelines or real-time adverse event profiles.
Oh.
It extracts the most relevant paragraphs from that database, invisibly pastes those paragraphs into your prompt, and then instructs the AI. Answer the user's question using only this provided text.
So RAG is that same medical student, but now they're taking an open book exam.
Exactly.
They still have their foundational understanding of medicine to help them read and interpret the material, but they're looking up the absolute latest verified dosing recommendations right there in the exam room before they write down their answer.
What's fascinating here is how that open book concept pushes us toward the ultimate goal. If Step 2 is the open book exam, Step 3, which is agentic AI, is the fully funded research assistant running the lab.
Oh, wow. Okay.
This is where advanced AI enters routine practice. An agentic model doesn't just produce a text response. It has an internal logic loop where it reasons about the data, plans a sequence of steps, invokes external software tools, evaluates the output of those tools, and then revises its strategy.
Here's where it gets really interesting. How exactly does it plan that sequence? Like, what is the actual mechanism making it an agent rather than just a really good search engine?
It uses a framework often called reasoning and acting. So when you give an agentic AI a complex goal like, prepare a summary for this patient's tumor board, it doesn't just try to write the whole thing at once.
It breaks it down.
Exactly. It breaks the goal down into discrete steps. It might generate an internal thought. First, I need to know the patient's current kidney function.
Okay, that makes sense.
It then generates an action, writing a query to the hospital's lab system API to actually pull the latest creatinine levels. It observes the result, then generates its next thought. Kidney function is low. Next action. Open the medical calculator tool to adjust the chemotherapy dosage.
Oh, that is wild.
Yeah, it iteratively loops through thinking, acting, and observing until the full task is completed.
So it's actively coordinating external software. It's reading the histology report, realizing it needs more information, and then actively invoking a separate specialized pathology algorithm to, say, predict microsatellite instability.
Yes, and then it translates all that into the free text criteria needed to check if the patient is eligible for a specific clinical trial.
That is a massive amount of administrative heavy lifting.
And it structures the output according to international standards like OncoKB guidelines. So it generates a transparent rationale for why a patient should or shouldn't receive a specific targeted therapy.
But wait, if these agents are actively writing code to query APIs, running calculators, and pulling lab results, The immediate question I have is, do we just let them run wild in the hospital's electronic health record system?
Yeah, that's the scary part.
Because giving an AI administrative access to poke around a fragile hospital database sounds like a recipe for a catastrophic IT failure.
Oh, absolutely. And this raises an important question about the barriers to deployment, which Truhn and Kather map out in really stark detail. The reality is that hospital IT infrastructure is incredibly fragmented.
To put it mildly.
Right. Data is locked in silos across different vendors, guarded tightly for privacy and security. Systems share data only through very narrow, fragile interfaces, and access is controlled by strict user roles.
Yeah, you can't just drop an autonomous agent into a network built in 2005.
You really cannot. Any AI assistant has to operate within strict, predefined guardrails, and more importantly, anything the system does requires a full audit log and version control.
It has to show its math.
It has to show everything. The system must explicitly record the exact question asked, the specific databases consulted, the precise software tools it invoked, the exact version of the model running, and even a mathematical estimate of its confidence.
Because without that granular transparency, investigating a medical error just becomes impossible. But let's play devil's advocate. Let's say a massive, well-funded research hospital manages to build all those IT interfaces and audit logs perfectly. Their agentic AI is running flawlessly. The paper introduces this concept of domain shift.
Yes, domain shift is huge.
If it works perfectly at a place like Mayo Clinic or Johns Hopkins, shouldn't it work just as well at a community clinic down the road? I mean, cancer is cancer. The biology of a tumor doesn't change just because you cross state lines.
Well, the biology doesn't change, but the data representing that biology changes drastically.
How so?
Different hospitals have entirely different note-writing cultures. Physicians use different shorthand. Laboratory panels have different reference ranges. Even in pathology, different hospitals use varying chemical staining protocols.
Oh, right.
Which means the exact same tissue sample will look slightly different under a microscope depending on where you are. Furthermore, they buy their imaging scanners from different vendors, creating minute variations in image resolution and color balance.
So a model trained entirely on Johns Hopkins data learns the subtle, specific patterns of how Johns Hopkins doctors write and exactly what shade of pink their specific slide scanners produce.
Precisely. All of those subtle local variations basically confuse a model trained in a different environment.
That makes a lot of sense.
Yeah, when you move it to a community clinic, the extraction accuracy just drops. The AI might silently start missing key diagnoses simply because the new hospital scanner has a slightly different contrast ratio, which throws off the internal mathematics of the neural network.
It's like learning to drive a car perfectly in your quiet hometown. You know where every pothole is, the rhythm of the traffic lights, the exact width of the lanes.
Right.
But then you fly to a foreign country, you rent a car, and suddenly the steering wheel is on the right side, the street signs use completely different iconography, and the local drivers follow this totally unwritten set of rules.
That is exactly what it is.
You understand the fundamental mechanics of operating a vehicle, but the context has shifted so drastically that you are highly likely to crash.
And that contextual shift is why standard leaderboard benchmarks, where AI models are ranked in a vacuum on static data sets, they are essentially useless for judging clinical readiness. You have to prove the model can drive safely in the new city.
Okay, so how do you do that without risking patient safety?
Through perspective, multi-center evaluation using what the authors call silent clinical studies.
Oh, also known as shadow mode.
Exactly. You deploy the agentic AI into the new hospital's infrastructure, and you let it run live on incoming data. It reads the files, invokes its tools, and produces tumor board summaries. But that output is strictly quarantined. It is never shown to the clinician.
So it's just practicing in the background, no harm, no foul.
Right. Then researchers take the AI's quarantined output and compare it against the actual ground truth, which is the final signed reports generated by the human experts at that specific hospital. You rigorously evaluate if the AI's extraction accuracy holds up against the local shorthand and local imaging equipment, and you only graduate the system to a live clinician-facing interface once its performance stabilizes across those diverse local settings.
Okay, so that handles the IT infrastructure and the local data variations. But we still have to confront the inherent risks of the AI model itself. Going back to step 2, where we gave the AI an open book through retrieval augmented generation, does pulling in external documents actually cure the hallucination problem?
Well, RHE significantly reduces hallucinations, but it definitely does not eliminate them. The vulnerability just shifts.
Shifts how?
It shifts from making things up out of thin air to misinterpreting the retrieved data. The model might successfully pull the correct clinical guideline, but the neural network might misattribute a sentence from paragraph A to a concept in paragraph B.
Oh, I see.
Yeah. Or it might paraphrase a complex conditional rule in a way that accidentally alters its medical meaning. Or honestly, it might just get confused by dense tables and mix up similar drug names or contraindications.
That's terrifying.
Right.
If the model can still confidently hallucinate a drug dosage based on a misread table, how do we protect the patient? Because we can't expect a doctor to double-check every single mathematical calculation the AI does behind the scenes.
No, we can't. And that protection really comes down to rigorous user interface design. The system architecture must enforce an evidence before conclusion protocol.
What does that look like?
The UI cannot just present the final answer. It must display the exact cited passages, visually highlight the specific clause of the guideline it used, and present the raw mathematical inputs of any calculation before the clinician even reads the final recommendation.
Ah, so show your work first, so the doctor can verify the logic at a glance.
Furthermore, the agent must be programmed with an abstention protocol. If the retrieved evidence is thin or contradictory or just missing, the AI needs to be trained to explicitly state, "I lack sufficient context to formulate a plan."
Rather than attempting to guess the missing pieces.
Exactly. It has to escalate the task to a human.
Which introduces a massive regulatory headache. I mean, where does an AI assistant end and a highly regulated medical device begin?
Yeah, that's the million-dollar question. The regulatory boundary really hinges on execution and autonomy.
Okay.
If the agent is purely retrieving passages and drafting a narrative summary for a human doctor to review, edit, and sign, well, it operates largely as an assistive documentation tool. But the moment that agent begins writing discrete, executable data back into the electronic health record.
Like actively proposing an executable order for a chemotherapy drug.
Exactly. It crosses the line. It becomes a medical device subject to intense oversight. Under the EU AI Act, systems proposing treatments are classified as high risk.
And in the U.S.?
In the U.S., the FDA applies software as a medical device rules because the outputs directly influence therapeutic action. This means a hospital can't just push a software update to the AI over the weekend.
Oh, wow.
Yeah, every model version change requires strict regression testing and a traceable regulatory approval path, just like modifying a drug formulary.
That regulatory friction is totally necessary, but it also points directly to the human element to this equation. Even if the UI forces the AI to show its work, humans suffer from alert fatigue.
We do.
If this agentic AI is right 99% of the time, the natural human tendency is to just stop checking the math. How do we prevent doctors from just blindly clicking accept on whatever the screen proposes, allowing that 1% hallucination to slip right into the patient's record?
You are describing automation bias, which the authors identify as a critical long-term risk.
Right.
And there is also the compounding danger of de-skilling.
De-skilling.
Yeah, if junior physicians rely entirely on AI summaries from day one, they may never develop the deep, intuitive, clinical pattern matching skills we discussed earlier.
Oh, wow, that's a really good point.
So to combat this, the system must be designed with intentional friction. High-risk actions cannot be a single click. They require conscious, multi-step confirmation.
So we have this massive transition ahead of us. We need to solve the IT fragmentation, run silent shadow studies for domain shift, build friction into the UI to stop automation bias, and navigate the FDA. Truhn and Kather outline a very pragmatic, step-by-step path for institutions to actually survive this transition.
Right. They do. They map a 3-step adoption trajectory. Step 1 addresses the immediate crisis, which is shadow IT.
Right.
Because EHRs are currently so cumbersome, clinicians are already desperate for help and are using public non-secure AI chat tools on their phones to draft clinical letters.
Which is a catastrophic privacy risk.
Exactly. So the first mandatory step for any hospital is providing sanctioned, private alternative tools that explicitly protect protected health information. Stop the bleeding of shadow IT.
Makes sense. What's step 2?
Step 2 is embedding dedicated narrow assistants directly inside the electronic health record. These are tools with modest abilities, like basic ARG functionality and medical calculators, that can draft notes with citations, but fundamentally cannot take any action without a human physically hitting approve.
And once that is stabilized and trusted?
Step 3 is the deep integration of the event-driven agents we discussed. This is the fully realized system where, say, a new molecular pathology result arriving from the lab automatically triggers the AI to wake up, analyze the new data against the patient's history, and propose an updated tumor board summary before the doctor even opens the file.
But to get to step 3, to build these highly capable medically accurate agents, we need significantly better AI models. And the paper makes it clear that the ultimate bottleneck preventing those better models isn't computing power.
No, it's not.
It's curated oncology training data. An agent can only learn the nuance of oncology if we feed it massive, well-curated, multimodal data sets.
The limiting region is really high-quality human supervision. The model needs to see the notes, the radiology images, the genomic profiles, and the longitudinal outcomes all linked together and verified by experts.
So what does this all mean for you listening right now? Because there's a detail in this paper that completely reframes the daily grind of practicing medicine.
Yeah, this is my favorite part.
The authors point out that when it comes to fine-tuning these advanced models, the most valuable training labels don't come from a lab. They live in routine clinical edits. Every single time a clinician reviews an AI-generated draft and makes a correction, every strike-through of a redundant sentence, every time you manually fix a slightly misclassified tumor grade, that action is a high-value supervision signal.
It is the ultimate ground truth data. When you correct the machine, you are explicitly mapping the boundary between mathematical probability and actual clinical reality.
Your daily administrative annoyances, your routine corrections of the medical record, they're not just busy work anymore. If your hospital has the proper data governance and explicit consent in place, your daily edits are literally training the future of oncology AI.
Exactly.
You are actively teaching the neural network how to think, how to weigh evidence, and how to operate like a human expert.
Which perfectly synthesizes the core thesis of Truhn and Kather's roadmap. The destination we are driving toward is augmentation, not automation.
Augmentation, not automation.
Right. The ultimate goal is a tireless learning assistant that handles the massive information synthesis, shows its mathematical work, and improves routine care while leaving the final, nuanced clinical judgment exactly where it belongs, with the human physician.
That is the perfect summary. Thank you for joining us for this deep dive into the mechanics and the future of generative AI in oncology. But before we sign off, I want to leave you with a final thought to mull over.
Oh, I love these.
Something that builds on that concept of the strike-through. If our daily edits, our highly personal clinical corrections, become the ultimate training data for the next generation of AI agents, who actually owns that collective clinical intuition?
Wow.
Right. If a model is fine-tuned exclusively on the specific edits of the oncologists at one specific hospital over several years, will that hospital's AI eventually develop its own distinct clinical personality?
That's a fascinating question.
Will an AI trained by doctors in New York make slightly different semantic choices or weigh risks slightly differently than an AI trained by doctors in London simply because of the specific human instincts that shaped its neural pathways?
We're no longer just passing medical knowledge down through static textbooks or lectures. We are actively imprinting our collective clinical instincts directly into the code.
It is a wild frontier. Keep asking those hard questions, keep correcting the record, and keep demanding that these systems show their work. We will catch you on the next Journal Club.